hexadecimal representation of an unsigned integer is a representation that uses base 16. In other words, the positional number system for each individual digit gets associated with a 16 to a power. So far, we've seen two other representations. One of those is called a decimal representation, and the other one is called a binary representation. In the decimal representation, we have these individual decimal digits, d sub k. Each of those were corresponding to a position in this representation, and then the position number captured in the subscript was identical to the power of base 10. Decimal means base 10. Each of those digits could be part of the decimal digit numbering system, which was 0, 1, 2, all the way to 9. 9 is 1 less than 10, and we talked about that in a previous video. On the other hand, we saw this thing called a binary representation, where we have these binary digits, in other words called bits. If we have an m-bit binary representation, we start at the lowest bit or the least significant bit that has b sub 0. Then B1, B2, all the way to Bm minus 1. The subscript value on each of those digits corresponds with the power on base 2. Each of the bits could be chosen from the set of possible binary digits, which includes 0 and 1. The upper bound, the last symbol in that set, was 1 less from the base. So here's the claim or the question. If we're using these patterns to define decimal and binary representations, could you guess what pattern we use to define hexadecimal representation? Well, base 10 decimal, every time we see a power, the base on that power is 10. Base 2, every time we see a power, the base is 2. Could you guess what it means to be hexadecimal? Yeah, these bases would change to 16. Also, instead of the individual digits being labeled as B for binary or D for decimal, maybe we want to label them as H for hexadecimal. The same idea though, the index would be powers of 16. And then the last question would be, where does each H get chosen from? What is the set of hexadecimal digits that we could possibly choose? That question leads natural into a guess about the general form for an unsigned hexadecimal representation. Let's begin with an unsigned integer, a non-negative whole counting number, and we'll say that an L-digit hexadecimal representation takes the form y equals h sub L minus 1, h sub L minus 2, all the way down h2, h1, h0, where each of these hexadecimal digits is associated to the corresponding power of base 16. Hexadecimal means we're using base 16. So the least significant digit, h0, would get paired with 16 to the 0. The second least significant digit, h1, would get matched with 16 to the first power, since the subscript value marks the position and is identical to the power of the base we're using in this representation. We can continue all the way to the nth digit in position L minus 1. That position number corresponds to the power of 16, L minus 1, and this gives us our hexadecimal representation. But the question that we were just asking is, what are the possible values of the actual digits that we have, each h sub I? And these are going to be chosen from the set of hexadecimal digits. The interesting thing, though, is that in standard written English, the largest number script that we use is the number 9. But in each number system, our symbols have to be able to count up to 1 less than the base. 1 less than 16 is 15, so we need 15 different symbols to represent numbers in our hexadecimal system. Computer science traditionally just borrowed some letters. So the idea here, the set of hexadecimal digits, we're going to say it's equal to 0, 1, 2, 3, 4, 5, all the way to 9. Now we don't have a single symbol for 10, so we're just going to borrow the letter A. So the letter A represents the decimal number 10. The letter B represents the decimal number 11. The letter C represents 12, D 13, E 14, and F 15. In other words, in our hexadecimal representation, each hexadecimal digit can be one of 16 different values starting at 0 going all the way up to F. This immediately means we can actually add to the table that we studied in the last video. Notice we had these first 15 decimal numbers and we can convert those into a 4-bit binary string. That's what we were talking about last time. But the claim that we're making now is that in hexadecimal, each of these decimal numbers is represented with a single symbol, the possible digit value for each hexadecimal position. The first 10 of these are not very interesting, but the last 6 are extremely fascinating in the sense that we're using symbols to represent decimal digits. As we'll see in this video, there is a very deep connection between these 4-bit binary strings and the corresponding digit. I will say now, I do expect each of you that are studying this to memorize this table. It is worth your time. We'll talk more about that as we get deeper into it. For now, this is just an introduction to this idea, but every time we see an A, that represents the number 10. Every time we see a B, 11, C, 12, D, 13, E, 14, and F, 15. Of course, one of the best ways to get our head around how this is working is to take a look at multiple examples and really explore those deeply. We'll start with example 1, where we're looking at an unsigned integer y1 whose hexadecimal value is equal to 9. We know this is a hexadecimal value because we're using parentheses in our subscript. That subscript tells me this representation is with respect to base 16. Well, this is a 1 hexadecimal digit representation, so 1 digit corresponds to position 0. So we'll call H0 equal to 9. Remember, the index on my digit corresponds with the power or position number of that digit. So 9 in hexadecimal corresponds to 9 in decimal. This literally means take 9 times 16 to the position number, 16 to the 0. We know that 16 to the 0 is 1, 9 times 1 is 9, so 9 in hexadecimal is identical to 9 in decimal, which we've already seen is 1001 in binary. 9 is 1001. Let's level up to really our first interesting example of hexadecimal. We'll take a look at an unsigned integer whose hexadecimal representation is D. This is base 16, which we see exactly here, and there's only 1 hexadecimal digit. The moment we know that this is base 16, we know that this digit stores a coefficient in front of 16 to a power. The power on 16 is identical to the index or the position on that digit. In that case, it's 0. So the actual value represented by this number is going to be D times 16 to the 0. But we know D in hexadecimal corresponds to, well, let's look at our table. 13 in decimal. 16 to the 0 is 1. 13 times 1 is 13 in decimal. But we've already seen in a previous video that 13 is equal to 1101 in binary. So now the single number 13 in decimal, D in hexadecimal, and 1101 in binary has 3 different representations, but notice they all encode the same value, the same number underneath. They're just different ways of expressing it. If you're confused by this idea, my claim is that your lived experience actually gives you insight to this. We have the same idea in human language. So for example, I can think of 3 different ways to say the word number. Number in English, numero in Spanish, and bango in Japanese. The word itself is represented by different letters, different pronunciations, different cultures, but the underlying idea of a number remains the same across the different representations. And that's the same idea here. The actual underlying unsigned integer 13, the value of that is the same. It's like counting to 13 on your fingers. It's just the way that we're expressing those values is different, or another way to say that is we're encoding the actual value using different bases. Hexadecimal uses 16, decimal uses 10, binary uses base 2. Let's take a look at yet a third example. In this case, we'll have the unsigned integer whose hexadecimal representation is 64. Notice those are 2 hexadecimal digits, H1 and H0. Here's my least significant digit and my most significant digit. The index value on each of those digits is identical to the position number, which identifies the power of 16 that I use in each case. So in this situation, 6 is in position 1, so that's going to get mapped with 16 to the 1. 4 is in position 0, so that gets mapped with 16 to the 0. So the number 64 in base 16 is equivalent to 6 times 16 plus 4 times 1. That's exactly what we see here. 6 times 16 is 96. 4 times 1 is 4. 96 plus 4 is, ding, 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 100 in base 10, which is identical to 1100100 in base 2. I want to show you something fascinating that arises from this particular example. Notice that we could say that the 64 base 16 has 2 hexadecimal digits. Now pretend I was going to write that as an 8-bit string of binary digits. So 6 in binary would be 0110. We could see that from our table on screen, or we could recognize that 4 plus 2 is 6. Remember that each position in a binary number represents powers of 2. 6 has 0 powers of 1, has 1 factor of 2, and 1 factor of 4. On the other hand, 4 has 0 of 1, 0 of 2, and 1 of 4, none of 8. So literally, to translate from hexadecimal into binary, I take each individual digit and just look at its binary representation. Another way to say that is, if I just looked at the binary representation of 6, that's 0110. We could see that from this table on screen. 6 is 0110. And then if I look at the binary representation of 4, that's 0100. So literally all I did is I just took each individual digit, put in the 4-bit code for the binary representation, and those two things are identical. That's actually a pretty deep fact, and we're going to leverage that heavily in this course, but I wanted to call your attention very early on in the process because this is very powerful. We can use this to understand what's going on under the hood in MATLAB, and we will do so many times throughout this course. Let's keep exploring and do one last example. So we'll look at the number y4, which in base 16 is given by 4 hexadecimal digits. Those are 1FFF. Remember, 4 hexadecimal digits means that the leading position value is 3. This is H3, H2, H1, H0. The index value represents the corresponding power of 16 that we mark with each of those hexadecimal digits. In other words, 1 gets mapped to 16 to the third since it's H3. F gets mapped to 16 squared. This F gets mapped to 16 to the first, and then the final least significant F gets mapped to 16 to the 0. Of course, we're going to multiply each scalar factor by its corresponding power and then add the results. That is indeed an inner product, which is why I like to say that all numeric representations that we study in this class are actually vectors in disguise. It's just freaking amazing, isn't it? So now what we're going to do is try to represent each of these in the appropriate decimal representation. 1 in hexadecimal represents 1 in decimal. 16 to the third, well, I can just go ahead and get the power of 16 table that I carry around in my pocket in daily life, and I know that 16 to the third is 4096. So this would become 1 times 4096 plus F. F is 15 in decimal, and then 16 squared, I know that that is 256. Then I have another F, which is 15. 16 to the first is 16. Then I have a final F times 1. When I add all those numbers up, well, first I guess I have to multiply. 1 times 4096 is 4096. 15 times 256 is 3840. 15 times 16 is 240. And 15 times 1 is 15. Don't trust me, you can use MATLAB to confirm my calculations. When I add all those up, notice that I get 8191 in decimal. I challenge you to do that in binary. If you start laughing and notice that this is actually going to be, let's see, 4, 8, 12, a 16-bit binary number, you would be exactly right. In fact, if we extend the observation that we made on our previous example, each of these hexadecimal digits has a binary representation. So let's do the 4-bit binary representation for 1. We know that the 4-bit binary representation for 1 is 0001. The 4-bit binary representation for F, well, right now we're going to actually use our table, but my claim is I highly encourage you to memorize this. Of course, you could also have the options of getting this tattooed on your forearm, and yes, if you get a tattoo of the decimal 4-bit binary hexadecimal table on your forearm, you can use that in any test that you ever want, and it won't be cheating because you're never going to forget that. Regardless, we know that F is given by 1111, so now I have 1111, 1111, 1111. In other words, if I wanted to convert 1FFF, all I do is just put those 4-bit strings together and I get the number 0001, 1111, 1111, 1111, and that gives me my binary representation. to complement the decimal and hexadecimal. Of course, I would say, please don't trust me. I'm a mischievous mathematician and I like to play tricks on you, so please do confirm this. In fact, we can do that in MATLAB. So let's set y4 to equal to 8191. We've already seen that we can actually run des2bin function on y4 to get the binary representation of that. But also there's this function in MATLAB called des2hex, and that actually allows us to translate decimal numbers into hexadecimal numbers. If I run this code, notice that, yeah, I hope you're a little upset with me. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, you got it? And then indeed I have 1 FFF, which is the exact number that we have. Here the function des2hex produces capital letters rather than lowercase, but they're using the same values. One really fun thing is you could actually open des2hex and take a look at the source code for this. I don't think that this is a native MATLAB. I don't think they paid software developers to do this. Maybe they got it from the community. Here, if you look at these lines of code, the first, let's see, it looks like the first 76 lines of code, maybe not. Yeah, so it looks like maybe the first 63 lines of code are all either comments or error checking, and then the real work starts somewhere at the bottom. So I encourage you to go ahead and try to read this. I could claim that this would probably, if I really wanted to understand this, it would probably take me like 8 working hours, and I'd probably do it over like a period of 3 days. So I'm not so worried about you parsing this code and understanding for yourself, but it is a fun thing to know that you could actually uncover what des2bin does and look at the source code if you want to, which is exactly what we've done here. Of course, we talked about previously that we want to check our work. So right now we know that h4 stores a string, which is a hexadecimal number. There's also this function called hex2des. If I type in h4 on that thing, I can get back to the original decimal number that I started with. Now, as a preview of coming attractions, remember that the entire discussion that we're doing in this unit is on unsigned integers, and this corresponds with MATLAB's numeric data class, which is the unsigned integer data classes. In fact, there are exactly 4 of those. There's uint8, uint16, uint32, and uint64. Here's a description of each of those and then the number of bits dedicated. And the claim that I'm going to make is underneath the hood, MATLAB is literally storing numeric data using binary representations of those unsigned integers. So for an 8-bit integer, that's a total of 7 positions. So starting at B7 all the way to B0. For 16-bit integers, that starts at B15 going all the way to B0, and then 32 starts at B31, 64 starts at B63. Here I'm going to do something really interesting and actually typecast this Y4 using 16 binary digits, or bits. And so I'm going to say that Y is equal to uint16 of Y4. When I run this, notice that the actual value entered here is the same, but this is where things get fun. I know, they've been fun the whole time. We're going to go ahead and format hex. Okay, so format hex is going to change the output from regular scientific notation into hexadecimal representation, but that hexadecimal is going to show us the binary string stored in memory, and this is where things are going to get crazy. So check this out. When I type Y4, I get this string of hexadecimal digits, but if I type Y, I get 1 FFF, which is exactly what we've just seen. And so my question for you is, what the hell is going on with Y4? We can get some insights to that question by looking at the workspace. Let's go ahead and maximize this worksheet or restore the value of it and then double click to see the whole thing. If we look at Y, we know that Y is stored as a uint16, but Y4 is stored as a double. And my claim is that the encoding mechanism that we use for doubles is actually really subtle and depends on what we call floating point representation, which we're going to get to, I promise. On the flip side, uint16 are literally unsigned binary representations, in this case with 16 bits. We're going to talk a lot more about what this means, but I wanted to show you why we're going into this, because all of a sudden we're starting to peel back the hood of these integer data classes using the knowledge that we've just covered about decimal, binary, and hexadecimal representations. That leads me into my community challenge for this video, which is to list words that you can write in hexadecimal notation and also the corresponding values of those words. We'll see much more about this as we move on. Thank you so much for your attention. I, of course, always welcome your questions, comments, and concerns in the comment section below. When you give me feedback, I grow and become more effective to serve you.